So, okay, so model validation. So this is one that I was working on earlier today. So, okay, so validation. So what is important to validate why is it important to validate your model? So I kind of give it like a scenario. And I think this is, for the record too, model validation goes beyond just linear regression. Validation is also for any types of machine learning models, statistical learning model. So I kind of like have a little analogy here. So consider like a class of students, right? And as the teacher, right, what would you do to ensure that the students learn the material for the final test? So you're going to have a final test at the very end, you know, of like the semester or like at the end of the unit or whatever you're doing, you're teaching. And you want to make sure that they actually learn the material for that test, and then you're going to test them. How would you test their knowledge? Like, how would you kind of make sure they're practicing and basically know that they actually did learn that information? So just kind of consider it. You don't have to like think out, you don't have to say anything out loud. Just kind of think about like what you would do as a teacher and probably from your own experience and stuff. And then also think about like the ways this could really fail, right? Like if you had a teacher, like basically think of the ways that you would cheat the system as a student. Okay. Just kind of think about that as we kind of go through. So some bad ideas, right? So there's plenty of bad ideas. I'm sure you guys can think about like how you could like not encourage the students to be best prepared for the final test. So I kind of gave a couple of things, and this kind of relates a little bit to like how we have to think about like modeling. So in this scenario, like relating to like machine learning and modeling and stuff like this, you can imagine like you as the designer of the model, right, is the teacher. You basically are providing this information, and your code are the students, right? So your linear regression is like a student. And the way you basically, let's see here, you are not adjusting like the coefficients by hand, right? Like you basically say, here's the data, here's the model, learn from this data, right? And see how well you do, right? And the way you see how well they do is like, oh, like an R-squared or MSE or something like that, okay? So the first bad idea that you can have with your data, so you have all this data in here, or let's talk about being a teacher, is you just literally give the students the final test with the answers. So you say, okay, the final test is going to be this test, and you just give them the final test and give them all the answers. What's wrong with this?
They're just going to memorize.
Exactly, right? They're going to memorize it, right? Like, wouldn't you? Like, if you knew that was the final test and that was all the answers, you'd memorize this, right? So yeah, obviously this is backfires. This is kind of equivalent to basically saying you give all the data, let's say you have this data set, right? And you give all the data, right, to your machine learning model, in this case, linear regression, right? You design the model and stuff like this, and you give all the data to it. It's going to learn off of all of the data. Remember when you do like a dot fit and stuff like that? It's going to basically take in all the data and try to fit the best line it possibly can onto that data. The problem is now, how do you know it did a good job, or if you're overfitting? How do you know basically that it's not just memorizing the answers because it just happens to be for the data set, right? So that's kind of what we're trying to avoid. And this is kind of the equivalent of being like giving your final test with the answers, because it's like, by definition, linear regression is going to try to find the best answer on this data. And you have to figure out like, well, okay, how do I know it's actually doing the best job, or it's just by pure chance that it's finding this weird way? For example, let's say you have a weird feature that's like how many squirrels there are in like a square acre of Canada, you know, relate like, let's say 50 miles directly north of like a specific area that you're looking at, and then you're predicting the house price. Like clearly that has nothing to do with it, but maybe by pure chance you might actually have that, and it's going to, the machine learning model is going to try to find the best possible answer or relationship to that. So that's what we want to avoid. So another better idea, but it's still not the best. So one is kind of closer to probably like what you might have, is you give students a practice test with answers, right? So not the literal final test, but like a practice test, right? And tell them that the test will be like these practice tests. Okay, so how can this backfire? What are some potential issues with this? It's subtle, but so one thing you might have, for example, if you, I don't know about you guys, if you guys remember back like in schooling, especially when you had practice tests, and this is, okay, so one problem is if you give a practice test, they might just like literally learn that practice test and not try to generalize past that, right? And so funny enough, I actually had this exact experience like in like university. And so it was like a university physics class and stuff like that, very smart people. And a lot of my friends, they found practice tests or a test from like year prior from the same professor, same class. And they used that, or no, maybe, no, I'm sorry. The professor actually gave out this test, like said, oh, this is where you can find my last year's tests. And they studied off of this. Well, for whatever reason, like I missed this information. I didn't know that practice tests existed. So what I had to do instead, I had to like read the book and go through my homeworks and stuff like that and like try to study out. I was studying on my own in this type case. And I remember literally on the day of the tests, they said like, oh yeah, did you look at the practice? Like say, oh, what did you get the answer for the practice test? Like, what are you talking about? And they're like, oh, the test from last year, he gave it to us and you could like look at the answers. And like, I'm like, wait, what? Like, I was like, oh no, like I'm so unprepared for this test. Like I did not look at this at all. And the funny thing is that when we actually took the test and we got our grades back, turned out I actually ended up doing a little bit better, not to like brag, but like I actually did a little bit better than like my friends. And part of the reason why is because a lot of the stuff that was on the practice test wasn't exactly like the real test itself. And people actually complained, well, not complain, but the professor's like, oh, like, hey, why did you give us this practice test? Like, that was just practice. He's like, that's not what the real test is supposed to look like. And so that's kind of the idea here too, is that if you give someone like a practice test like this, problem is like they might just try to memorize that practice test and then try to apply it to the final test and they're not going to do a great job, right? So that's kind of the equivalent of what we're going to talk about, like a holdout validation, where basically you have your practice test and you have your practice test and you look at your practice tests and you learn from that kind of thing. You kind of iterate, try to get better and better on this. And then you try to go over to your real test. And the problem is that now you didn't have a real way to evaluate yourself on these practice tests. And you basically went to like, again, like overfitting, using the terminology, we're overfitting on this practice test. And then when we try to get the real test over here, it's like, oh, it didn't work very well. When I say practice test, that's kind of, you should think in your mind, train sets. So like you'll see like X train, Y train, right? That's your training set. And so what we want to do is be able to say, okay, we have practice tests because this obviously is a good idea. We don't want the real test at the end, right? We don't want to look at all the data, right? But we want to basically have some way to kind of basically test out how well we're doing. And so a solution to this, and it's a little subtle this, and this is where kind of made an analogy kind of breaks down, but basically we instead like have the students practice these little smaller tests, and then the teacher like will lead like another like practice, overall test. And so not the final test, but something like this. So the students know how well they're doing on studying. And that way they can say, okay, like we study off of these practice tests, they go off of that, and then they have like the teacher led, pop quiz or, kind of equivalent to that. And they can adjust, say, oh, well, I actually need to study this more and stuff like this. And this way they can kind of do this over and over and over again. And they can get better at like the final tests. Now, we don't have that exact analogy here, but that's going to be closer to cross-validation. And so we'll talk a little bit about this. So I'm just going to give you guys like an idea of like what this would look like and like why this works. Okay, cool. You guys cool if I keep going then for holdout validation and everything? All right, so holdout validation. So this is the stuff that basically, oops, I had a little to do here, but I did that. Okay, so holdout validation basically comes with, and I'm just going to draw on my screen because it's a little bit easier for me just saying this. My draw, sorry, my draw tool is like really on the bottom of my screen. There we go. Okay, so imagine you have your full data set like this. So imagine each imagine like each column here is like a data point, okay? And we have our full data set. This is our full data set. And what we can do with holdout validation is say, okay, well, this is all the data we have, but we wanna know if we did a good job on our model, did our model generalize? One thing you can do is say, okay, we take say like 80% of the data and save that to basically train our model off of. And we save this last 20%. We hold this out and we don't train off of this. Basically what we do, we try to adjust our model better and better off of this data here. So like 80% of the data. And we test our model on this data set and say, okay, like, like we got an R squared of let's say 0.6. Like, oh, that wasn't very good. Like, let's try again, like maybe readjust the model and we get an R squared of like 0.7 and 0.8. We get better and better at training on this model. And then once we say, okay, I think we look pretty good now. Let's see how well we did against this thing. So basically you train or fit. So no, if I say train and fit, that's basically the same thing. We're training off of this data. Okay, so basically we're seeing how well, like how good of an R squared we can actually get. And then we just say, okay, based on the model that we trained, right? So we have the coefficients now for the linear regression. We pass that model in there and say, okay, now we have these features from here, and we know that we have the answers on here, but we never trained on it. Let's see how good of an R-squared value we have. And so with this R-squared value, it's like, okay, well, it's like, let's say we had our training, right? And we can get R-squared values of like, let's say we have R-squared values of like 80%, right? So like 0.8, right? But then we tried doing with this, holdout validation set, right? So this is sometimes called the test set. But like we hold this out here and we test against it. It's like, oh, our R-squared value was only 0.6. Okay, it's like, ooh, that wasn't very good, right? This was very good over here, but this wasn't good over here. So what you might try doing then, right? Well, what do you do at this point, right? Do you just say, oh, I guess my model sucks. Like, the model's no good. Like, do I just like stop there? What would you probably want to do?
Maybe split it a different way and retrain it.
Ooh, good. That's exactly what we're going to do in cross-validation. But you skipped over what I was actually going to say. So maybe before that, you might say, we'll redo the model, right? We redo the model and then see how well, let's say we do this model again and we get a different type of model, but it's also getting like R-squared of like 0.8, right? And then we test it against, our holdout validation. It's like, oh, we have an R-squared now of like 0.7. Well, the thing is though, Jessica's way probably actually makes a lot of sense, and we'll talk about like why that is. But the problem with this is that now you're starting to indirectly overfit onto this set that you've never seen before. Like you're not supposed to be training off of this. You're kind of inferring and saying, is my model good by training it off of this data, but then like almost it's like validating it, right? To see like, is my model actually good on this data? So the problem is if you keep doing this back and forth, back and forth, back and forth, right? You will eventually indirectly, right, hopefully get better scores on here, but you're now starting to overfit. So that's part of the issue. There's also issues of like, well, let me ask you guys, let's say we do this at the very beginning, we split this off, right, that 20%. What's some issues about like saying we only train off of this data and then never look at this data until like we have it fully trained? I think of like any potential issues.
I mean, there could be some data that is important to learn, but we pulled it out of the rest of the training set, and we never got a chance to train on it.
Right, exactly. So imagine there's some like, special things that are in this testing set over here, this 20% that, for example, let's say like we're predicting the price of a house, right? And let's say let's say color is a huge factor of like how much the house is going to cost, but almost all the blue houses are all in this data set, right? Well, now the stuff we trained off of would have seen a blue house, right? And it wouldn't know what to do with this information over here. So that's kind of like an issue, right? Depending how you split it might actually affect what your kind of training is. So we're kind of missing out on this, basically holding out some of that information. Oh, like it would be really useful if you actually knew this. Okay. So yeah, these are some issues. So it's still not a bad idea, right? Like doing this validation. It's better than just looking at the whole data set. That's the worst case scenario, because basically you would have no way to check if you actually are doing a better job in your model or generalizing. So I wrote this little scenario here. So basically I'm just pulling out some data from that's built into sklearn, a data set. It's about like California houses and stuff like this with different features. And so I'm just pulling out the first 1,000 data points because it's like 40,000. So it's a little bit easier for us to see. And I'm just going to go ahead and show you guys pair plots of this data set. And there's some different features and stuff. And basically what I'm going to do is, once this loads, pair plot kind of takes a while. So there it goes. So you can see there's all these different features. I know you guys can't see this very well. It doesn't really matter what the features are. But basically I'm going to pull out a specific feature. In this case, I'm actually going to pull out the third feature. In this case, it's the average rooms. So average number of rooms in like, this area and whatnot. And then we're going to try to predict the price. So when we actually pull this out right here with, right here, our target, it actually has my data.target. We'll see this stuff again. So I'm going to see if I can predict Y, price. And you can see here, if I looked at all the data for, let's say, just one feature, in this case, average rooms, right? So average rooms on the x-axis, and then the y-axis is the price, okay? You can kind of see, like, okay, there's a general like trend here, but we don't want to look at all this stuff, right? So if we did like a holdout, right, we can use sklearn's model selection train split, or train test split. You guys seen this already so far? maybe, okay, see some nods, see some check, that's okay. So you guys will see this for sure. So this is a really classic one to basically split your data. So what I can do is test train split will basically return 4 different arrays, like NumPy arrays of your X train. So this is your training data. And then we have our X tests. So X with the capital usually referring to the features, right? So like X is our features, Y being the target. And so this basically is all the data that we'll use for training. And this will be all the data that we'll use to test it. And this will be the Y, the labels of that training, and then the Y of the test. And then this train test split here, I'm passing in the features, the labels. So usually you'll see it denoted as capital X, comma, lowercase y. And then this test size here, basically how big should this test be? We can actually specify either the train size or the test size, and usually about 20% to maybe 10%. It depends on how big your data set is, but usually between 5 to 20% of your data will be reserved for testing. So that's kind of like the holdout validation. Like we're going to hold on to this and not look at this until we want to basically check out, how well our model did. I put a random state here, but you can actually put a random state. But since what I'm doing here is actually trying to basically split in different ways, you'll see how it doesn't quite work out. Like it depends how you split it, right? But for the record, you should always do a random state if you have an option. That way it's consistent and it's easy to find like the same split. I put the shuffle equals true. That's already the default thing. So what I'm doing here is I'm going to split this 10 times. So basically I have the full data set and I'm going to randomly split it where 20% of the data is going to be my test set and 80% of my data is going to be my train set. And then I'm going to do it again, splitting it randomly again, right? 20% over here, 80% over here, and doing that over and over again 10 times. I'm just going to save those results to be like all of my train sets, all of my test sets. Okay, that way I can kind of like compare them. And so I just create this little function to make it easier. And so again, I'm only using like specifically that one label, which was the average rooms. So just make it a little bit easier so we can actually see this. So I'm actually going to create this. And so right here with this test and trains, basically just this test set is a tuple of like my X train, Y trains for each situation. So there's going to be 10 of them. So just to show you guys, so it's a little bit easier. Oh, this is going to be, well, let's do shape. Oh, it's a list, right? Sorry. Well, if I do this, it's a little confusing. So you can see here, it's 10 different ones. And then inside this test set, there's going to be a tuple of your my X train and my, well, in this case, my X test and my Y test. Okay. Makes sense? I just want you guys to know what this looks like. Okay, cool. Stop me if you guys have questions.
So it kind of looks like cross-validation, except there's more randomness in it, right?
Kind of. We're actually gonna, yeah, it's more random essentially. It's like as if if I gave you this assignment to 10 different people, they would split it 10 different ways. So that's kind of like what we're doing. Right. So let's pretend like there's 10 of you guys. We're gonna have 10 different ways you guys split this thing and compare this. Yeah, cool. And I saw, I think Jessica, you raised your hand.
I was going to ask a question, but I think I realized that as soon as I was going to ask it, I was going to ask for clarification, like why you didn't use random state, but it's because you need like different ones each time. So
that's right. That's right. Yeah, I want it to be random. So if I put random state, it would be the same exact, random set every single time, which would be less interesting. All right. So to show you guys a little bit, I'm just going to show you guys the different, the different test sets. So basically each of these different test sets, and you can see how some of these, for example, include some of these extra outliers, some of them don't. And so you can see is that depending on how you split your trained test, right, you might have different results and stuff like this. So that's one big issue about this. Like if you imagine now like your linear regression fit on here, if I actually show you the train sets, right, which are going to be more values, it's going to be like 800 values. You can see here, it's, you can tell the most, like if you see like where it's darker, like for example, you can see this is pretty like, a little bit over here, but this one has less points. In this case, you can see like these outliers were not included in this train set. So you can imagine, this might be an issue where you are losing like, for some information about things that you never trained on. So this kind of stinks, right? It's like, oh, like I would like to see all the data. So that's where cross-validation kind of comes in. And this is where Alvaro kind of mentions like, oh, this is kind of going to cross-validation. And that's exactly it. So one thing to note with k-fold cross-validation. So I think the curriculum actually points directly from here. Basically, if you imagine like, here's all my data. So this is kind of where you typically see this data kind of split up when you talk about cross-validation. So here's all of my data. And then what we do, we split it still. right? So this would be like a holdout validation. It's like, oh, here's all my training data and here's all my testing data, right? And so the thing is, we're only going to train off of this thing and then test it against here. Well, okay, like, you know, we have some issues with this, but at least, you know, we're like, okay, like we can say, oh, we've never seen this before. So you still want to have this part. This is the holdout, like you've never looked at it before. You still want to use that as kind of like your testing benchmark. And then we have all our training here. And you can think of our training data as all the stuff we're ever going to look at to actually see how well our model performs. So the thing is though, we also want to avoid, I'm just going to write in here, we want to avoid using our training data and like, you know, getting some, you know, special model. I won't use this rectangle like this. I'm trying to do something nice. There we go. Let's say we have our model M. Okay. We have our training model, right? And then we test our training model on the test data set, right? And then the thing is like, well, when we test it and stuff like that, it's like, oh, it didn't do very well. Then we have to retrain our model and stuff like this. We would start fitting on this test data set, which isn't great. We really want to just test this once, right? This is kind of like your final test to know how well did your model do? How well do your students actually know the material? Imagine if a teacher let you take your final test over and over and over and over again, right? Like, even if they don't know the exact answers to the final test, like they can start figuring out, you know, what was a good thing and what was a bad thing, right? So we only want to do this once. So we hold this out right here, and we call this our test data. And then what we do, I'll just keep this here. What we do, we have our full training data, and we create different folds, K folds. So K meaning like how many folds we have. So in this case, we have a K fold of 5. And essentially what we do, we try to treat this like training data set as a little mini kind of like training test. And essentially what we do is like, okay, this very first split right here, our model is going to use all of this data right here, fold 2 through 5, to train off of it, right? So let's say pretend like you are seeing like, okay, you have the model, what you think will work really well, right? Like you have your certain interaction features and all this interesting stuff, right? You have this like idea of what your model is going to be, your linear regression, like your hyperparameters are going to be. And say, okay, let's see how well it does. And you basically train it off of all this. You're going to have different coefficients now for all of like the linear regression like model. And then you test it off of this fold 1. So this is usually called your validation set. So validation, or sometimes it's also called dev. So your dev set. So what this is right here, basically, it's not your testing set, but it's to help you validate to see how well your model does. And then what you do, you say, okay, I did this well. Let's say your R squared in this case was like, I don't know, 0.72. Okay. Then what we do, we train it again on the split number 2, where we only use the green, fold 1, fold 3, fold 4, fold 5, and validate it, right? We only train on these green parts and validate it with this blue, fold 2. And again, maybe this R squared is not going to be 0.72. Maybe it's a little bit better. Maybe it's like, oh, you know, we actually ended up getting like a 0.74 or something like that. And then the next split's like we do it again. We're like, oh, you know, training on or validating on fold 3 here, you get like an R squared of like 0.68 or something like that. And you do that for however many folds you have. So the idea here is that now we can see like, hey, like how well did our model do overall training off of different segments of this data set? And then how well did it validate? If your data seems to be like your R squared seems to be pretty close to each other, like consistently around 0.7, then you can feel pretty certain like, hey, based off of this training data here, assuming your training data is very similar to your test data over here, we can probably feel pretty confident it's probably gonna be very close to this testing data, right? If you have different parts where your R squared is all over the place, you're like, oh man, like this isn't very good. Or your R squared is too low and it's like, oh, we need to do a different model. You can then retrain it on top of all this stuff, make adjustments to your model and retrain it. And you basically are making a little tiny like practice tests for yourself. The nice thing is that students remember everything. The model's gonna forget every single time you retrain it, right? So the idea here is that you can basically make little tiny practice tests and see how well it does. And then say, okay, this is looking really good. You know, ideally you would have already trained it, but you could go back now, say, okay, take all of the training data, train off of the whole thing. So now it knows everything, case of all the K folds. You have now your model, and then you do your final evaluation against your test set. And you only do this once. So the idea here is that basically the idea is that you hope that your test data will give you your final example of like how well this does. In production, in the real world, what this would be like new data that you have never seen before. So maybe, for example, if you have a self-driving car, you know, you would basically train off the data you already have, right? Doing Holdout validation, see how well it works. And then your test data would be new data that it's never seen before to see how well it does and how well it performs. You want to have this test data. The worst thing you can do is leak what we call data leakage. If we leak some of this information into this training stuff, because then it's going to see some of this data ahead of time, and we don't want that. We want to know, you know, what's that final test look like. Okay. Does that make sense? Give me a thumbs up if this is sounding pretty good. Sideways, thumbs down. Any questions, any clarifications or comments? Okay. So I want to clarify, because I think a lot of times people get really confused, like, what is cross-validation? Cross-validation is not meant to train your model. Your cross-validation is to validate how well you're training, right? So in the end, you're still going to train off of all of this data, but your cross-validation is saying, okay, we train off all this data. You now think that you're pretty confident, like, I think it's a good model. Use cross-validation to validate that you have a good model. Okay. And then at the very end, you test it against your test set. Cool. Yeah, Nadine.
Sorry if this is a bit obvious, but I'm just sort of lost in the process. What step do you do the split from your training test? Is it before you do all the like transformations, or is it like just in the sort of like model?
You're talking about like this split right here, right?
Yeah. So do you straight away you got your data? Do you first split it and then start examining it and doing EDA and everything, or do you do it later on?
Yeah. So ideally, you want to do this as early as possible. So you want to try to avoid as much as possible checking out this test data. So what you might do, what a lot of people will do, they'll do an initial EDA of just like, okay, like what does, you know, what's in this data set? And then they'll split it across here. If you're being really careful, which, you know, you would split this off and never look at this test data. However, this can be an issue too, because imagine if your test data has other values that you never considered and stuff like this. So that's why usually we do a quick EDA just to kind of see what are different values we can have and make sure, because ideally we want to make sure our training data does reflect what's in the testing data itself, but we don't want to look too closely at the testing data, otherwise we might bias it ourselves, right? So there's kind of a fine line. In the real world too, you might not ever be able to look at new testing data until literally it's time to test it out. So this is something, you know, when you make models that are robust and stuff. But if you had like categories, let's say these are like your different houses and stuff like this, like different colors, and there's like another color that it's never seen before. If you tried using your model in here, it's not gonna be able to know how to encode this test data over here. And we'll talk more and more about this in machine learning too, because there's sklearn pipelines that can help us, allow us to more carefully split the data and do the same transformation so we get those same results and not get those weird errors. So in the project in general, I would say, don't worry, like if, you know, on our one-on-ones, you know, we can talk about how we do this test set and we can talk about like, you know, how you can do this. But really, I would rather you guys focus like, you know, this is kind of like a little, not exactly real practice, but trying out all this training data, but try a cross-validation to see, you know, how all this works. You can, if you'd like, to try out this little bit of test data. You might split the data set and just get like the last 10% and keep that at the very end. But I'd say for you guys, you know, starting off, because we haven't learned all the tools, do your EDA for the most part with your whole data set, and then keep that last 10% for your holdout test. Okay. Cool, good question. Yeah, and let's see. So I know we have about 5 minutes left. So just real quick before anyone heads out, I'm going to show you guys Kaggle in a second. And we're actually going to have a Kaggle competition, like as a cohort and stuff. And what's really cool is that Kaggle really does allow you to really see this training versus your test data. So I'm going to walk you guys through that and what that looks like. And then maybe in the future, if you guys want to use a Kaggle or participate in Kaggle competitions and stuff like this, you know, to enhance your skills and stuff, you kind of know the general format. Okay. But before I go into that, any last questions about anything we talked about today?